force problems where we've just had an object pulled to the right by one guy and a force to the left by another guy. And we've done multi-force problems where we've had elevators or vertical problems with gravity acting down and the normal force acting up. And we've done multi-force problems where we've had pulleys. Sometimes even a couple pulleys like this. Now we're going to do multi-force problems that look more like example number 9, where we have what we call an inclined plane. It's a fancy physics term for a hill. We have hills, or we have inclined planes. The angle of this hill is 30 degrees. We have a 22 kilogram object on the side of this hill with this incline, and there's a force of friction acting up the hill of 20 newtons. How does friction act up the hill? Well, in the absence of friction, which way would this box move? Down the hill. Okay, which way does friction act? Up the hill to oppose that motion down the hill. What force pulls this object down the hill? If you're telling me that it's going to move down the hill in the absence of friction, what force acts down the hill? Gravity? Not exactly. I always thought gravity acted down. In fact, it does, right? Gravity does act down. So gravity doesn't directly pull it down the hill, although it is a part of it. Any other forces that act here that could cause it to move down the hill? Pardon me? The incline, it's part of it. Yeah. The normal force pushes up, right? Not here, the normal force doesn't push up. The normal force pushes at, do you guys remember? 90 degrees. Well, that doesn't really push it down the hill, does it? Watch what I'm about to do. You're going to see in a moment that it's actually gravity and the normal force, ironically the normal force that kind of pushes it up, that pulls it down the hill. Gravity and the normal force combined. Okay, let me erase that and then redraw it. Two forces acting here, besides friction. There's gravity acting down. I'm going to draw that straight down. Gravity will always act straight down toward the center of the earth. It doesn't matter what the incline of the hill is, gravity acts down. That's the easier one because it's always acting down. The normal force acts perpendicular to the surface. Now I could draw that normal force right here. It's fine. But it might be more convenient for me to draw that normal force here. Do you see that that's the same thing? Whether I draw it above the surface or below the surface doesn't make any difference as long as I have it drawn in the right direction. I have it drawn 90 degrees to the surface here. If this is our surface, my normal force is drawn at 90 degrees perpendicular to the surface. Let's label that. Now, what do you see here? You see two vectors, a normal force and a force of gravity drawn head to tail. We could turn that into a vector diagram. The sum of those two forces, if we add the normal force and the force of gravity together, in other words, find the resultant vector joining the start to the finish, look at the force I get. It's a force that is parallel to the hill. I'm going to call it F parallel. The normal force and gravity combined, added together, vectorially added together, gives me F parallel, which is the force that drags this box down the hill. I'm going to redraw that F parallel up here. It's not like there's two of them. There's only one F parallel. I'm just drawing it in two different places. I'm going to solve for it down here in my triangle, and then I'm going to use it up here where I have it drawn next to the force of friction. You can imagine, if I can get the value of F parallel, I get two forces left, F parallel and FF, and it's an easy question at that point. The challenge is to get F parallel. All right, let's figure out how to find F parallel. Before I do that, though, let me emphasize one point. You need to draw this so that this angle right here is 90 degrees. Think about that. Think about that. F parallel is parallel to the hill. F normal is perpendicular to the hill. So F parallel and F normal have to be perpendicular to each other. Does that make sense? They have to be. If you have it drawn like this, and some people will draw it like this, you will get this question wrong. F parallel, right here, must be drawn parallel to the hill. and it must be perpendicular to the normal force. If you draw it the second way that I drew it, you're going to end up using the wrong trig function, and you're going to end up solving for the wrong answer. Now, the next thing is this, guys. Here, let me make this a little bit bigger just so you can see the angle involved here. This is 30 degrees, right? This is gravity acting down. This is the normal force that is perpendicular. And this is what we're looking for right here, F parallel. I ended up drawing that normal force a little bit too long, so I'm just going to erase it now. In order to figure out what F parallel is, we have to figure out what this angle is right here. Now, tell me what this angle is between this and the normal force here. What angle is this right in here? That's 90 degrees, right? Great, make sense? That's 90 degrees. Okay. What's this angle right here between gravity and this imaginary line right here? That's 90 degrees as well. If this is 30 and this is 90, then this angle will be what? 60. All the angles inside a triangle have to be 180, right? 30 plus 60 plus 90 is 180. Okay, if that's 60 and this one is 90, then what's this one going to be? What's this angle in here going to be? 30 degrees, right? 90 minus 60 is 30 degrees. The good news is that angle right here will always be the same as the angle of the hill, always. It'll always be, if the hill is 30 degrees, that's going to be 30. If the hill is 40, then that's going to be 40. Yeah, I've showed you why that's the case, but in the end, it's always the same. Okay, off to the side here, now, off to the side, we're going to find F parallel. I'm going to say sine 30 degrees is equal to opposite, which is F parallel, over hypotenuse, which is the force of gravity. Force of gravity, the force of gravity is m times g, 2 times 9.81 times sine 30. 2 times 9.81 times sine 30 gives me, I think it's just 9.81 actually. Just a coincidence. Now, that's not my final answer, right? But it is F parallel, which means I've done the hard part. What are we going to focus on now? This. I'm going to say F net is equal to the sum of the forces, F parallel plus FF. And then I'm going to solve. Solve for the acceleration, just like we have in all those other questions we've done. How is it? Somebody try to give me a good answer for this question. How is it that I can arbitrarily not count the normal force and force of gravity? They don't cancel here, right? They do not cancel. How is it that I don't have to count gravity and the normal force when I'm adding these forces together, F parallel plus FF? That's a bit of a trick question too. Scott? Yeah, I am counting Fn and Fg, right? When I say F parallel, that is Fn plus Fg. Marcos asked a question a little while ago about combining forces, and I said, I caution against that, right? Well, that's exactly what I'm doing here, right? I'm saying F parallel plus FF is equal to the net force. Well, really, F parallel is the vector sum of Fn and Fg. I'm really combining those. It's just that, Marcos, in this case, I feel like I have to. It's not just an option. I feel like I have to there. Does that make sense? Okay, the net force now is m times a. So we're going to say ma is equal to F parallel plus FF. M is 2. A is what we're looking for, F parallel. I want to say F parallel is down the hill. I'm going to make it negative 9.81. The force of friction is 20 Newton. Wait a second. Can friction acting up the hill be bigger than the force down the hill? Why not? It's moving down the hill. Friction acts up the hill. What's going to happen to this as it moves down the hill? It's going to slow down. And eventually it's going to stop, right? And then there isn't going to be any static friction or any kinetic friction anymore, and then it would be static. That's a whole different problem. All right, negative 9.81 plus 20 is 10.19. 10 divided by 2 is 5 point, what is that? 5.1? Somebody got a number for me there? 10.19 divided by 2 gives me a value of 5.09 or 5.10. What's similar about this question as compared to other questions that we've done? Well, most of it, to be honest. All of this is the same, right? F net is equal to the sum of the forces. That's what we do with all of them. What's different about it? The only thing different about this question is this, F parallel. If you can get F parallel by finding the vector sum of the normal force and gravity, and we do that with the sine function, then this question just turns into any other question. In fact, I would say that it turns into a pretty easy question once we get F parallel. It's not easy, don't get me wrong here. I'm not saying that if you have trouble with this, then you're having trouble with an easy question. It's not an easy question. But once you get F parallel, once you get the value of F parallel, then it's an easy question. Okay? Does this diagram make sense to everybody up here? This analysis up here, sine 30 or sine law or whatever some of you are going to do? All right? Let's tackle it then. Specifically, let's tackle on your worksheet, the worksheet you were working on, questions 11. Let's go 11 to 13. 11, 12, and 13. Try to get number 11 done in the next couple minutes. It'd be nice if we could actually do this one in class together after you've had a chance to work on it before you go home, just for another little refresher, okay? One more little piece of advice here before you really start working. The example that I gave you, there's a reason why I gave it to you. It's so that you can have something to look off of. Like, don't try to tackle those 3 questions I just assigned without looking at this example. You will mess up. Most of you will mess up if you do. This is a recipe. This example is a recipe. When you're baking a cake, what do? You follow the recipe. When you've baked 1,000 cakes, sometimes you can bake the cake without looking at the recipe anymore, right? But when you're trying to bake the first cake on your own without somebody showing you how to do it, what do? Look at the recipe. Every time, right? Look at the recipe. So don't be afraid to look at this recipe. Once you get really good at it, then maybe you don't have to look at the recipe anymore. But right now you do. If you don't have this completely written down, then write it down and then follow the recipe.